4, but it bears repeating. If you have like a degree 4 polynomial, like this is, then it will have 4 solutions. This has at most 4 real solutions because you could have imaginary. Of the 4 roots, which ones? How many are imaginary? This one here, which means the other are real. Okay. And so once again, it could have all 4 real, but if it could have none real in this case. If it's odd, by the way, we'll see this later, but if it's odd, we said it half cross the x-axis once, didn't we? But if it's even, it might not cross the x-axis at all, which means an odd one have to have 1 real root, and even one doesn't. This one does. This one has 3 roots, but it could in theory have all imaginary. Now, there's conditions on that theorem, by the way. One more thing. Of these 4 roots, which one is considered a rational number? The 7 and only the 7. The others are irrational. You cannot express them as ratios of 2 integers. But 7 can. You can write it 7 over 1. And so, which leads into this. We're talking about the rational zeros theorem. Before I explain what all that means, just look at this. And actually find this in your notes. Now, I can't ask you to factor this because it's not complete. But you know the factors must start with either a 2x or an x. Yes? What must they end with? A what or a what? A 1 or a 3. Yes? So your possibilities are like 2x plus 1, 2x plus 3, x plus 1, and x plus 3. I think it's all the different possible factors you can come up with. Now, if it may be like it's positive, if I made it possible that it could be negative, then that'd be more possible. That's good enough. Now let's talk about the possible zeros then. X plus 1 using negative 1 is 0, right? What else do you have? This gives you negative 3. This gives you, and I'm using negative 1 half, 3 halves. So they're fine. What I want you to do is actually write all these possible zeros as fractions. So take the number, put them over 1 so they look like fractions. Okay? And first of all, I want you to focus on just the numerators of all those fractions. Well, they all have either 1 or 3 as a numerator. What does that have to do with our original polynomial? Well, they're all factors of that constant, aren't they? The numerators are. And all the denominators, with all either 1 or 2, which means all the denominators are factors of the coefficient. And it always works that way, which is what the rational root theorem says. It says if you have a polynomial, then every rational zero, and notice it only speaks to rational zeros. It says nothing about any imaginary zeros or irrational zeros, just the rational ones. But if it does have rational zeros, then it'll all be, it can all be expressed as a ratio of 2 numbers. And I would draw these arrows. P, the letter P is irrelevant. The point is, that's a factor, one of the factors of the constant. Whereas the denominator is a factor of the coefficient. That's always going to be true. In our example, all the numerators are factors of the 3, the constant, all the denominators are factors of the 2, the coefficient. And there's some conditions on here. P and Q can have no common factors. So that's our theorem. So here, look at this example. So what you do to find this, the bottom list here, here's our actual list of possible rational roots. They call the rational zeros theorem, but I call the rational roots theorem because it's rotary. Anyway, you list all the factors of the 12. And notice you make them all plus or minus out there. Then list the factors of the coefficient, that's what this is. And then you put one of these, you do every possible combination of one of these factors over one of these factors, in that order. Well, also, if you do 1 over 1, that's that. 2 over 1 is the 2. 3 over 1 is the 3, and so forth. That's where this first part comes from. Then you go back and put all these numbers over the 3. Well, 1 over 3 is where the 1/3 came from. 2 over 3 is 2/3. 3 over 3, we already had. Then 4 over 3 gives you 4/3. 6 over 3 is 2 again. 12 over 3 is 4 again, and there you go. That's how that looks came about. Okay? So here, let's do this. I'll get back to this. On this first example, we're going to start by listing the possible rational roots. What I would do is come over here and list the roots of the constant there. List the roots of the coefficients there. And then I don't always label this, but this time I think we should. This is our list of possible rational roots. can take these numbers over here, put them over 1 first. 1 over 1 is 1, 3 over 1 is 3, 9 over 1 is 9. Put them to plus and minus, and then go back and put them all over 2. 1 over 2, 3 over 2, and 9 over 2. And that is our complete list of possible rational roots. If it has rational roots, it will be one of those, what is that, 12 numbers? And then how do we find out if any of those are rational roots? By dividing and seeing if the remainder is 0. Now, usually you don't have to do it 12 times before you find a root, okay? But even if you did, I want to put things into perspective. You have to understand, we were trying to factor and then therefore solve this polynomial. We have no method for factoring it. So you could start just testing random numbers. How many integers are there? A lot, infinite. How many fractions are there? You could argue more. Definitely, we can't really talk about it in those terms, but that list is very short compared to infinity. Yes? And so that's your first step. The theorem tells you the possibilities. You need to test them. Let me go back, actually. This is on your notes. First step I skipped over. Look at the degree to find out how many roots you're looking for altogether. Then list all the possibilities like you did. Then you test them, which is what we're doing now. So which one do you want to test first? The 9 halves or the 1? That's what I would choose. So put the 1 there. Put your coefficients. 2, 13, 29, 27, and 9. By the way, it's a degree 4 polynomial, so we should have 5 numbers in our expansion, right? And we do, so we don't have any need for any zeros. All right. Try this. 2, multiply, add, multiply, plus 1, add, 3, 4. I don't think we're going to get a remainder of 0 out of this, do you? It's just going to get bigger and bigger because everything's adding. So stop. The goal is not to test all those numbers. The goal is to find one that works and gives you a remainder of 0 as soon as possible. Okay, so I'm serious. As soon as you realize and you're sure it's not going to work out, just abandon that one and move on to the next one. That's our negative 1 next. I always go in that order. 1, negative 1, 3, negative 2, and so forth. So, all right, let's try this. 2, multiply, and multiply, 18, multiply, that. Look at that. It works. Good. So we found a root, a 0 of the function, right? Or essentially, we just divided by x plus 1, didn't we? Okay, so we found a factor. Now, let me go back and read the last step, 3b. It says each time that a 0 in this factor is found, repeat the previous step on the depressed equation. So we successfully divided. This is our depressed equation. By the way, what is this? This is 2x to the power of what? Right? Because it's originally degree 4, so our answer is degree 3 now. And what it says is, try that same root again on the depressed equation because it might work again. Because you can have repeated roots. In other words, we said x plus 1 is a factor, but it could be true that it's x plus 1 squared or cubed. Couldn't it? So I'm saying, once you find one that works, you try it again. I'll just put it right there. Because it might work again. And then let's see, 2, multiply, add, multiply, add, and lo and behold, it does work again. Okay? So the negative 1 turns out it works twice. So listen, you can continue this process, but what we have now is quadratic, isn't it? Stop the process because you don't need it anymore. You've been trained in dealing with quadratics. You know how to factor quadratics. So rather than going through and testing this long list, don't. Just factor it. And look, obviously you need 2x and x. And then what do we do? 1 and 9, 9 and 1, or 3 and 3? 50 plus 3, 50 plus 3. And we're done. We have to write up our answer. We wanted the factor form of the polynomial and the zeros. I like to do the factor form first, actually. So we got x plus 1. Get that as a factor. And we get 2x plus 3. We have x plus 3. Now, Now, there's a problem, hopefully arise, because we're supposed to have degree 4 answer. And yeah, the x plus 1, the negative 1 is a repeated root, which means that's supposed to be an x plus 1 squared. So good. Notice this one, pay attention, all right? And then list your zeros. Negative 1 has multiplicity 2. You need to write the multiplicity. There's various ways you can shorthand it. If you want to put like just m2 for multiplicity 2, I'm okay with that. And then this gives you negative 3 halves. And negative 3. There, that is your final answer. By the way, if you want to just put like negative 1 times 2 to indicate the multiplicity, or multi 2, something like that, but you need to tell me the multiplicity. Yeah, sure. Yeah, sure, that's fine. I'm fine. No, I don't use the multiplicity one. When I first introduced it, I did, but normally I don't. So, yeah, if you want to put multiplicity on 1 when it is, you can, but you don't. All right, we're done. Questions? All right, now look at this. So here's the answer we just got. But just for the record, all those solutions we found were from our list, right? We didn't find them all by testing, but they were actually all in the list, weren't they? Like the 3 halves was. We found it by using the factoring. Look at this graph, by the way. It's a correct graph, but it's scaled out. It looks like it doesn't match. What I mean is, like here, that's at negative 3. That fits, certainly. But here, it looks like it has an inflection point there. If I zoom in, you see that it actually is correct. We were correct. It's supposed to be negative 3 with multiplicity 1. That matches. You just cross it right there. It's supposed to be negative 1 with multiplicity of 2. It actually is. It was hard to, well, you couldn't see it before, but it does bounce there, doesn't it? And then the other solution was negative 3 halves. That's supposed to be a linear factor. And you got to understand, it does just go straight through. I'm sure, but it's not an inflection point. It doesn't bounce, so that is correct. Okay? Yeah. Yeah, remember, if you have a factor like this, you say it has a multiplicity of 2. So like if I gave you this equation in this form and asked you to graph it, you should realize, oh, okay, I have negative 1 with multiplicity of 2. And if you have that, then you're supposed to bounce when you hit that intercept. Okay? That's what's supposed to happen. And in this scale, you couldn't see that. Because actually you had 2 different zeros really close to each other, and you just couldn't see it until you zoomed in. And it does cross here like it should have, and it does bounce there like it should have. Okay? So I'm just saying, if you want to check your answers in the calculator, then be careful sometimes. All right, one more thing about this. Same problem, same situation, same roots, same polynomial. But here's another polynomial. And you see these, you both have these same roots, like negative 3 halves is the solution of this, for this, and this. Yes? Now, but this is not the right factor form for this. How do you know? Yeah, when you multiply out, you wouldn't have a 2x to the power 4. And also, besides which, when you multiply out, the constant wouldn't be 9. You can correct. And so this is not the same polynomial, all right? Just me. If I gave you the problem, and I will sometimes, if you've done it, or I said, all right, yeah, we've already done this actually. But if I gave the problem where I say, here's the zeros, write the polynomial, I don't want to see this, okay? I want to see polynomials like this, with whole numbers everywhere. Now, that being said, look, these are actually related. This one, like this one, this which is this, it's actually a vertical expansion by a factor of 2. If I took this equation times 2, I would get that equation. And watch, I just want you to see this. If it times by 2 out in front like that, now I've got technically 4 different factors. I have 2, then this, then this, and this. I'm just going to put these 2 next to each other. The 2 times that one. But isn't that equal to 2x plus 3? And you could do that. You could just write these factors and then realize you need to put a times 2 in the thing to get it to have, well, because that fraction times 2 to get it on there. And that'd be a way to get a factor like this. Anyway, let's move on. Now, a couple theorems. These are basic. This one says, basically, you can write every single problem as a quadratic, either all linear factors or sometimes irreducible quadratic. This is irreducible, it's prime, you can't factor it, that's all it means. So every problem, whether it's degree 3, 4, 5, 20, you can get it down to that level, all linear or quadratic. Okay? And so you're not done if you leave something as x cubed. The moral of the story, though. And then this I'd already mentioned. It says if you have an odd degree polynomial, then it has at least one real zero. And so it's even though it might not. All right, let's do this again. First, look at possible rational roots. List the factors of the 35 constant. List the factors over the coefficient. And then look these factors over those factors. So 1 over 1, 5 over 1, 7 over 1, 45 over 1. And put all these factors over the 2. So 1 over 2, 5 over 2, 7 over 2. I'm going to write it 10 times there. Now that is 16 different numbers technically, but you never have to test all 16. You know it to be actually 6 million. But you know that. One thing I want to emphasize again, though, listen. Like in our list, do you see 2 as one of those possibilities? No. Do you see 2 over 5, 2 over 7, 2 over 3? No. In other words, you don't just list all those multiples. You don't do these over these ever. It's always like we've been saying. Those numbers over those numbers, every possible combination, but always in that order, nothing else. Okay? All right, let's go. Let's test them. Push them out and it works. So what do we do now? Try it again. Try the one on the differential equation. That's the negatory. Now, so fine. We'll move on to the negative one. Still working on that first equation now, though. It's going out. 2, 13, 8, negative 35. I don't think so. Move on to 5. Three, 5 times 23, 15. I don't think so. Let's try negative 5. 4, 2, 13, 8, 5. 3, negative 15, so we add negative 7, and there we go. And now it's quadratic. If it started with degree 4 like we did, it's going to take 2 steps. Successfully dividing once gets you degree 3, again gets you quadratic, which is 2x squared plus 3x minus 7. Let's see, it's got to be 2x and x. It's going to be 1 and 7 or 7 and 1? 7 and 1? Let's see, that's 7x and 2x, which is actually 5x, which is not right. You can't factor. You can't. That is an irreducible quadratic factor, which means we're done. Factor form is easy. 1 means x minus 1 is a factor. Then that means x plus 5 is a factor. And then that's our other factor. That's what we just said. You can always break it into linear factors and or irreducible quadratic factors. Now we write our zeros. 1, negative 5. We'd have to find the solutions here. We can't do it by factoring, so we do it using this thing, which is known as the what? Quadratic formula. So it goes here, minus 4ac. There's a 2, but not there. Over here, down here is 2a. You're supposed to know that thing, okay? You're supposed to be able to handle quadratics whenever there's a limit. You either solve the factoring or solving using this. Now, I like doing the discriminant first, so I'm going to pull that off to the side. But b squared minus 4ac. A is 2, b is 3, c is negative 7. So 3 squared minus 4 times a 2 times c, which is negative 7. 39. 4 times 2 times negative 7. Well, 4 times 2 times is 8 times 7 to the 6. It becomes plus 2 to the 6. So 65 is the discriminant. Listen to me. That's the number that's going to go under the radical, right? I want you to realize that you should have expected it to be something that doesn't work out nicely. Like it wasn't going to be 64. If it had been 64, you get 8. Get a fraction, which means it was factorable. But it wasn't factorable. That's why we're doing it. If it had been negative, I mean, we have a measuring solution, right? So anyway, I'll just finish this. What goes here? Gives you the opposite of b, plus or minus that over 4 because it's 2a. Now listen, and you can't simplify this because square root of 65 can't be simplified. Yes. So you just write that on your answer blank. This time, I want to write it separately. In other words, I'm going to write negative 3 plus square root of 65 over 4 as one root, and negative 3 minus square root of 65 over 4 as a separate root. You don't have to write them separately. You can put them just together, plus or minus. But I wanted to be able to see that this was a degree 4 polynomial. Our answer, under our factor form, was a degree 4 polynomial. That's good. And we had 4 roots, of which how many of those were rational roots? The first 2. Those 2 are on our list of rational roots. The other 2 weren't, but they weren't rational, so they didn't have to be. The rational root theorem guarantees that if it has rational roots, they will be in that list that we generate. So that's all it says. Okay? Questions? Okay? Then you try this one. Listen, one thing I want to mention is we didn't find these last 2 by testing them, but they were in our list, weren't they? They had to be. Something I want to warn you against is, let's say you're doing this process and you messed up a negative 1, you didn't get your 0 like you're supposed to, so you think it's not a factor, so you move on. Well, in this case, it wouldn't be too bad, because when you get to negative 3, hopefully you don't mess up and find it is a 0, right? That's just, these are dangerous, I don't know. Obviously, they can suck up a lot of time, especially if you start messing it up. There won't be, it's not like there'll be a bunch of even tests. At most, 1 or 2 like this, where you have to do this whole long process, all these different stuff. Just asking you to list the possible rational roots is a valid test question just by itself. Making sure you can do some negative division is another test question. There won't be a whole bunch like this. We usually choose ones that don't take too long, but then if you do it wrong, it might take too long. But anyway, I want to put it in perspective. Yes? But once again, the process here, the thought process, with the limit term and the box method, you start the same way. You multiply a times c, so the negative 36 can go into 3 times negative 12, and then the 5 is the middle term. And then you fine tune orders that multiply to be that, but add to be the 5. And and once again, it had to be the 9 had to be a positive 1, 6 had to be a positive 5. And then once again, those represent how you split the middle term, and then you factor the group. Right now, before I talk about this, there's a couple of hints that can sometimes eliminate some of the possibilities, which is good. But I'll go back to those. I want to make sure I cover this. Now, find this example on your notes. And I have it twice. On the first time, it's written down, we're going to at least set it up as if we're going to do it the same way. Because we want to talk about that. You list the possibilities, so you have 1 over 2, and 1 and 2, and 1, 2, and 4. And you list your possibilities. I'm just going to write down, we test 1 first. What would I put here? 4, then what? 0. This is degree 4, so I should be writing down 5 numbers. 4, 0, 7, another 0, then -2. Because once again, our original did not have a degree 3 term or degree 1 term, which is why I put the 0s in those places. If you had messed that up, all that work would be for naught. So I would every single time say to yourself, okay, so before I should have 5 numbers. Get a little simple act, and you'll make a mistake, you'll catch a mistake before you waste all your time, okay? And then, frankly, I'm not going to go any further with this because I want to solve the fraction because you can. Once again, you only do that process if you can. But there's something that you can't factor, and do it that way. So here, this is one of the ones we've done before where you hopefully recognize that you can do the substitution. Once again, I call it x squared u, and then that becomes 7u, and that becomes 4u squared. Even though that is the correct factor, so we see it here. And then you get these. But those aren't the answers because we're trying to solve for x, right? So go a step further, and you say that means x squared is 1/4, and x squared is -2. Now the left-hand equation, that definitely has a solution, okay? If I take square root of both sides, let me show this properly. Take square root of both sides. This technically the value of what? 1/2. And then for this, you say, okay, I can either put 1/2 or -1/2 inside that value, or both work, so those are both solutions. I'm not really clear how you get the plus or minus 1/2, so that's technically how it looks. Now this other one, here's the deal. You can't get, like with real numbers, this is impossible, right? If the direction said, solve this equation over the real number system, find all the real solutions, anything like that where you only have to find real, then you just stop right there. But it didn't say that. So we're going to proceed. You should be able to. Same thing, take square root of both sides. You got the value of this equals, and isn't that really just I times square root of 2? Take square root of negative, so you get plus or minus I square root of 2. That's your other two solutions. Once again, it's degree 4, so it should have 4 roots. In case only 2 are real, the other 2 are imaginary. Okay? And listen, it didn't say anything, it just said solve the equation, right? So you don't have to look the factor form because it didn't ask for that. It didn't type a question. It's related, similar, but not exactly the same. All right, now look. These rules, they help you because look, we're finding bounds in the zeros, and so it says if A and B are your bounds, that means every zero falls between those, okay? Or maybe equal that. That's what we mean by bound. So here, look. In this theorem, it says that if you have x plus 1, then your number you're testing is -1, right? So if you're testing negative, like here's an example. So here's our polynomial, here's our long list of possibilities, okay? We just tested -3, and after testing -3, we focus on our output, or result, if you will. And the theorem says that if the row that contains the quotient remainder, these are what I circled, has entries that are alternately non-positive and non-negative. Now it says it that way because you can have 0 in there. But here, just watch real quick. If that happens, then you know the number you just tested is the lower bound. And if negative 3 is the lower bound, then what numbers do I not need to worry about? Negative 4, negative 6, negative 8. You don't have to test any of those because we just found, according to the theorem, negative 3 is the lowest number that could possibly work. And no, negative 4, negative 6, negative 8. Yeah. And then there's another theorem for if you test positive and it meets this condition, then it's upper bound. You don't have to test anything above that. So that can help eliminate options.